Hey, AP Chemisters, this is Mrs. Vandelay bringing you another edition of Blankwalle videos. This is chapter 15, section 6, part 2. Part 1 was determining what is the equilibrium concentrations if you have a strong acid. And I left off right before I hit, well, what happens if you have a weak acid, all right? So let's just begin right here then. So what if we have a weak acid? What do we know about the Ka of a weak acid? It's going to be pretty small. And it's going to be so small, it's typically going to be less than 10 to the negative fifth. And does that ring a bell? You remember what chapter 14 said? If K was very small, roughly 10 to the negative fifth, what can we do? We can assume that X is a small approximation. And I taught you saying, ich bin sehr fröhlich, yeah. That means we don't have to use the quadratic equation. We can make some assumptions, and that will make your life so much easier, okay? So how do I do this? Well, we have to list the major species in the solution. So keep in mind, will water take a part in this, all right? Does the self-ionization of water going to determine the pH? We need to keep that in mind. Choose a species that can produce the H+, write out the balance equations for the reaction that produces the H+. I think you can do that. You can show the ionization. And then it says, using the values of the equilibrium constants for the reactions that you have written, decide which equilibrium will dominate the producing the H+. Is it usually the water or the acid, okay? Write the equilibrium expressions for the dominant equilibrium. List the initial concentrations of the species participating in the dominant. Define the change needed to achieve, define X. Write the equilibrium concentrations in terms of X. Substitute the equilibrium concentrations into the equilibrium expression. And then solve for the X is the easy way by assuming that when you subtract it out, you get pretty much the same thing. Then finally, use the 5% rule to verify whether the approximation is valid, and then calculate the hydrogen concentration and the pH, okay? Folks, that's a lot of verbiage, isn't it? It is just like what we did in chapter 14. This is explaining everything that we did in chapter 14 with one little exception, and it's this, all right? So before we didn't specify, well, X was going to be the H+ concentration, and there was no pH in chapter 14. But everything else is just like what we did in chapter 14. So hopefully if you need to go back and see how we did that, we spent a day doing that. If you need to review it, then so be it. I think it'll come back to you, though. I really do. So let's try example letter A. Find the H+ and the pH of a 0.1 molar solution of acetic acid. Oh, look at the Ka value. It's 10 to the negative fifth. So ich bin sehr fröhlich. Yeah. All right, so let's go ahead and set this up, okay? All right, so here is my equation. Notice I have acetic acid, and I'm showing you the H+ is ionizing. And so here is my H+, here's my conjugate base. And now what do I need to do? I need to set up my ice table. Do you remember doing this earlier? I'll set up like that. So my initial concentration is 0.1, and I assume that these are zeros. They don't tell me I have any. So I'm going to subtract X, add X, add X. So I get 0.1 minus X, XX, okay? So now I believe, let's see here, we have done write the equilibrium expression, list the initial concentrations, we defined X. All right, now I'll write the equilibrium concentrations in terms of X. We've done all that. So now we're going to go into the equilibrium expression, all right? So let's go ahead and do that. So my equilibrium expression is products over reactants. Well, what am I going to do here? Well, Ka is equal to X squared over 0.1 minus X. Now, what is the beauty of this? All right, let me do this. What can I assume I can do? I can cancel this out. I'm going to assume that this is so small that it doesn't make any difference. Okay, so now what? All right, I multiply the Ka by 0.1, so I get X squared is equal to 1.8 times 10 to the negative 6. All right. Oops, I think I skipped a spot here. Sorry. Here, let me put this over here. There we go. And now we can assume that, here we go, X squared is equal to 1.8 times 10 to the negative 6. So what is X? Well, go ahead. You take the square root. What is the square root of this? I got 1.3 times 10 to the negative 3, okay? So how does this help me? All right, how did I define x? All right, so now I'm going to look back up here. All right, I solved the solve for x the easy way by assuming that, okay? So how did I define x? Well, I defined it as the h plus, right? Know what x is? And so, oh, what should I do the 5% rule? So what is 1.3 times 10 to the negative 3 divided by 0.1 is 0.012 times 100% is 1.2. So I'm still less than 5%. The 5% rule works. So now I can just go ahead and do the pH. I'm going to plug in the X value for the hydrogen ion concentration. I get pH is 2.89. Okay, so it's so similar to what we did in chapter 14. I remember telling you guys that this is the foundation of the next two chapters. Well, here it is, all right? Is setting up these ice tables. What made our life so much easier is that assumption where we can cancel out the 0.1 minus x, and then our math got so much easier, right? Well, guess what? We have several of these that we can practice on. So let's turn to the next page. All right, the hypochlorite ion has a high affinity for its protons, meaning it's a much stronger base than the chloride minus, and it forms a weakly acidic hypochlorous acid. Notice the Ka value, -8. All right, that is pretty small, isn't it? Calculate the H3O concentration, the pH of a 0.1 molar aqueous solution of hypochlorous acid. So I set this up for you, and what I'd like you to do is, seeing as how you're experts at setting up the ice table, go ahead and do this on your own, pause this, and only when you're done, come back, okay? So pause this, all right? All right, welcome back. Let's see how you did. Here's my ice table, all right? So again, it's 0.1 XX. And here's my equilibrium expression, okay, my law of mass action, if you would. And here's my Ka. It's equal to 3.5 times 10 to the negative 8. Now, what is it that we could do? Say, okay, we can cancel this out, right? So now what? I'm going to multiply both sides by 0.1, so x squared is 3.5 times 10 to the negative 9th. And now I took the square root of it, and I got 5.9 times 10 to the negative 5th. So what should I do? Quickly, the 5% rule. So what is 5.9 times 10 to the negative 5th divided by 0.1? You get 5.9 times 10 to the negative 4th. Multiply that by 100%. You get 5.9 times 10 to the negative 2nd percent, which is much, 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 much less than 5%. So we are good. Our assumption was certainly valid, all right? So now what's left to do? Well, now that I know what the x is, hey, how did I define x? It's equal to the H plus concentration, isn't it? Now how I defined x? Very important. So then I plug that number in, and I got 4.22. Now, what did you notice? Account for the facts that these problems each have, I'm scrolling down here, a 0.1 molar of the initial acid, but the pH values are very different. Why are they so different? Well, because you had different Ka values, you had different strengths of acid. So you notice that the Ka of the hypochlorous acid is much smaller than the Ka of the problem before. And so it's a weaker acid. The pH is going to be higher. It's not as acidic. Remember, the lower the number, the more acidic. So that's why the problem on the previous page had a higher pH value. Okay, so let's take a look at problem number 24. So it says find the pH of a 0.2 molar solution of nitrous acid with a Ka of 4.6 times 10 to the negative 4. Oh, that's not good. What does that mean? Oh, I have to use the quadratic. So, all right, well, I'm going to set up the ice table anyway. All right, here is my ice table. And I kind of cheated. I left out the initial thing, K equals H plus times NO2 minus over HNO2. So I guess I just kind of left that out. So here's my next step. And can I do anything with this? No, I really can't, sadly. So I'm going to have to use the quadratic, if you will. So this is what I did next. I multiplied both sides by 0.200 minus x, okay? And so then I have this. And now I just kind of rearranged it. So notice now I have x squared. and then I put the x term next, all right? I added 4.6 to both sides, and I subtracted 9.2 times 10 to the fifth from both sides. So what does this do for me? My a is 1, my b is 4.6 times 10 to the negative fourth, and my c is negative 9.2 times 10 to the negative fifth. So if you have your calculator handy dandy, or if you have your cell phone with the quadratic equation, app right there, you can solve for your x, and you're going to get two different terms. So the only one that made sense is this term. Okay, so if you want to go check my work, go right ahead. Okay, so then what? I went back and I kind of did a few shortcuts. I defined x as my h plus, and I got 0.0093. So I took the negative log of 0.0093, and I got 2.03. Okay, so that was kind of sad, wasn't it? Now notice that my Ka is higher than some of the other ones, and notice that my pH is then lower than some of them. Okay. All right, let's go to the next page and see what I'm going to do next. All right, so in letter B, find the H2O positive and the pH of a 0.0200 molar solution of nitrous acid. Again, the same Ka. Oh, das ist sehr traurig. That means that is so sad. Why don't you pause this, try this on your own, go ahead and you're going to use the quadratic again, and see what happens. So pause this, and when you're done, come back, okay? All right, let's see how you did. Maybe you're done. I hope so, because you're back, right? So here is what I did. I have to scroll down even some more, aren't I? So anyway, here is my ice table. And notice I have 0.020 minus xxx. Here is this. I wasn't lazy this time. And I have my x squared over 0.20 minus x equals this. I multiplied both sides by 0.02 minus x. I distributed. Notice that my exponents are a little bit different. And so then I put I added 4.6 times 10 to the fourth x to the left-hand side. I subtracted 9.2 times 10 to the sixth to the left-hand side. So here again, here's my A, B, and my C. And I got x is 0.003 when I'm all done. So I went back here again and said that's what my x value is. I found the pH is a negative log of 0.003, so I got pH of 2.52. Now, go back. What was the pH on the prior page? Oh, let's find out. So when the initial concentration is 0.2, all right, I got 2.03 as my pH. But when I start off with a lower initial concentration of 0.02, my pH went up. So let's answer this. What effect of lowering the initial concentration on pH? It becomes less acidic, doesn't it? The pH goes up, all right? So here it says, find the pH of weak acid in the cases where the X is small approximation does not work. It's the same thing as that we just did, all right? So here, let's go ahead and find the pH of a 0.1 molar chlorous acids with a Ka of, wow, that's a really high Ka, isn't it? It's not even close to 10 to the negative fifth, all right? So once again, ich bin sehr traurig. I am very sad. So why don't you go ahead and pause this and do the exact same thing as we've done the prior two cases, all right? So go for it, pause this, and when you're done, come back and see how you did, okay? All right, so this is what I did. Here's my ice table. Here is my law of mass action. Here is this. I multiply both sides by 0.1 minus x. I distributed it. I combined like terms. I get x equals 0.028. I plug that in. I got pH is 1.55. All right. Well, once again, I see it's about 15 minutes, so time is up. We're going to need a part 3. We may even need a part 4. We'll see what happens, all right? So I'll say this as always, don't wait to be great, and we'll see you shortly. Bye-bye.